Let's get this show on the road. Hello, everyone. Hope you're all well. Let's actually jump into. So the quizzes aren't done grading, as you know. So I'll probably finish tonight, but usually the turnaround is about a week. But I should probably finish by tonight. You should be able to see the answers. I don't know how through Gradescope, but I did check on show answers after the quiz was finished on Gradescope. So I'm assuming that there's some way to see the actual answers to the quiz. If you can't see it on Gradescope, I also posted a PDF version of the quiz with the answers on the class webpage, so you should be able to find that. Either way, you should be able to see the quiz and its answers, and I already mentioned in an email that you shouldn't just go directly to the answers, especially if you kind of found the quiz difficult or you ran out of time. You definitely want to know the class webpage as in on the CCNY math website. So normally when I say class webpage, I mean that page there that I just posted in the chat. So you go there, every time I give a quiz, I'll post a PDF version there as well as the answers there. So you can double check that. You should also be able to see it on Gradescope, but I don't know how to enter the student view on that, so I don't even know where to actually tell you to go, but I assume there's some way to see it. That being said, let's actually just jump into things because I actually want to teach you a new integration technique today, but we first have to wrap up trig substitution. So we're going to finish up with the examples that I asked you guys to try. Hopefully you tried them. Let's stop the camera and pay attention. So the important thing for trig substitution, I'm not going to go over it in too much detail, but just a small recap. The important thing is this table right here. Essentially, the idea is whenever we see expressions like these guys, a squared minus x squared, a squared plus x squared, or x squared minus a squared, it turns out that these trigonometric substitutions turn out to be convenient usually. What is convenient? Meaning, if it doesn't look like a basic rule, you can't simplify it to look like a basic rule, you can't do substitution, and you can't do integration by parts, then this will probably help you work it out by transforming an integral that does not have trigonometry into an integral that does have trigonometry. It's particularly useful when you see these expressions are trapped inside of radicals or things with weird powers in them. It's particularly useful in that case, but we actually did an example where that was not the case. So like this example here. But yeah, whenever you see these three kinds of expressions, you are pretty much always allowed to make these three kinds of respective substitutions. And this allows you to take the simplifying powers of our trig identities to apply to your integral. Now, of course, these are substitutions as usual, which means once you assume this equation, you have to differentiate that equation to get the differentials, substitute everything in your integral, and the hope is you can get a trig integral that is easier to deal with. You can use this diagram to do the back substitution. You'll get the answer in terms of trig functions or perhaps the angle, and you can solve for the angle from the original substitution, and you can solve for any of the other trig functions using this triangle that is constructed. Being able to figure out how to go from the trig function answer to the answer in the original variable using this guy is called a back substitution. Now, of course, I also mentioned, because in trigs, for when you're doing a trig substitution, the back substitution process itself can be long. It can also almost be as long as it was to figure out the answer to the integral in the first place. I do recommend that if you have a definite integral that you avoid doing the back substitution phase altogether. That being said, we did a couple examples here. See an example like this, and again, you would go through the strategy of trying to see if you could apply a basic rule, try to simplify, try to do a substitution, try to do integration by parts. But if none of that works, trig substitution is another option. As you guys can probably tell at this point, trig substitution is one of the longer methods out there. So it's really not something I would want you guys to apply unless you really had to apply it. You really have to kind of look for it and see, do I really need a trig substitution here? I would say it's one of those things that you should scarcely use if that's a thing to say. But once you realize that a trig substitution is possible and you don't really have an easier method, and to be honest, almost any other method we're going to do is going to be nicer than a trig substitution method, almost. And so if you can't do any other method, you can do that. By doing the substitution, you can differentiate to find the differentials. You plug into the original integral. The trig identities allow you to simplify the integral to get a simpler trig function. Hopefully that is an integral that you will be able to do. Once you do that, you'll get an answer. And once you have an answer, you can use the triangles to convert the answers in theta versions to their answers in the original variable version. And that's basically it. So we did several examples, but we do have a bunch more to cover because trig substitution is something that you'd want to get used to. It's probably going to take a little bit longer to get used to it than a regular substitution. And even that takes a couple days. So we're going to do a bunch more examples, and I actually wanted you guys to try. And then we're also going to talk about when you should do a trig substitution versus when you should actually avoid it. There are some situations in which we would avoid it, even though it's more than possible to do it. That being said, let's actually jump into this. And as I mentioned, I do want to teach you another technique today. So let's just try to make quick work of all these guys, and you guys can chime in and let me know what you tried so we can move on. Let's start with the first one. So this is the fourth example for trig substitution. And again, a regular substitution isn't going to work out here. Can't really simplify this. You have a sum under a radical and it's in the denominator. It's a very complicated function as far as integration is concerned, and no real way to simplify outside of it. So what did you guys actually do here? Okay, so complete the square. All right, so hopefully you remember, this thing isn't plugged in. Hopefully you remember how to complete the square. For some reason this thing, okay, there we go. It wasn't working. Completing the square was the trick here, if you can call it a trick. So here you have this expression. Now remember, okay, there you go, Fahim. Now you got it. Remember, to apply a trig substitution, you have to have one of these three types. You have to have a difference of squares or a sum of squares. You can't have three terms. Having a quadratic isn't good enough. You have to have a special kind of quadratic. Now, if you have a regular quadratic with three terms in it, and you want to get it into one of these, this kind of form, you can do that by completing the square. That's one of the uses of completing the square. Okay, so you see something like this. Of course, you would first think about substitution and all the other things, but if not, you try to see if a trig substitution can work. And here, to get that to work out, we would complete the square. So x plus 2 squared, because I know how to expand squares, I realize that this is going to give me x squared plus 4x plus 4. Now, for this, to get back the 8, I would add a 4. Right? Now, there are a couple ways to complete the square. I'm not going to go over that. That's something for algebra and pre-calc class. However, you can complete the square. You will then notice that you have a certain form. Specifically, you have x plus 2 squared plus 2 squared is what you have there. Well, a squared plus x squared and x squared plus a squared are exactly the same thing. Addition is commutative, so it doesn't actually matter. So here, notice here we have x squared, and this time the x, quotation, x squared plus a squared, where the x here is the phrase x plus 2, and your a is 2. That's your a. Right? So this allows us to do a trig substitution. So for this situation, what is the appropriate substitution?
X equals to a tan beta.
No. Nope, that's off by a little bit. I mean, tell me the specific situation. Don't give me the general rule. Tell me the specific substitution here. Right, x plus 2 is equal to 2 tan theta. Right? This is like your x, right? As in the x from the general formula. X from general formula. And then the 2 is the a. Right, and at that point, now it's just a substitution. So you differentiate both sides. And then you go back and you plug this into the integral. So this is going to look like, so this is 1. Your dx becomes 2 secant squared theta d theta. Under the radical, what we're going to have is we're going to have 4 tangent squared theta plus 4. By plugging in the x plus 2 is equal to 2 tangent theta. Now that, of course, simplifies into 4 secant squared. That's the whole point of us actually doing this substitution, to be able to simplify what's under the radical. Now this happens to be just 2 secant. So this is going to undo. So this whole thing is going to cancel the 2 and is going to cancel one of the secants. Right? Because under the denominator now we have 2 secant. And so we will have just the integral of secant theta d theta. That guy is now a basic rule, right? What is the integral of secant theta d theta?
I think you forgot the 2 when you were canceling out.
Where?
When you cancel out the 2 and the 4, isn't it supposed to be?
It's a radical 4. Right? Is there another 2 that I forgot?
I misunderstood.
Right, this whole thing here is just 2 secant theta when I apply the radical. So the 2 is going to cancel with this 2, and then the secant is going to cancel one of those secants. Okay, and the integral of secant is almost, Abdullah, you forgot the absolute value. So it's the absolute value of secant theta plus tangent theta. Now that's your answer in theta. You have to back substitute. What do we do? How do we get the back substitution working? The triangle, how do you set up the triangle? Okay, so we know that x plus 2 is 2 tangent theta. How do we use that? So you isolate the tangent. So the tangent then is going to be x plus 2 over 2. Right, that you know is opposite over adjacent. So you can form the triangle from that. So here's theta. The opposite is x plus 2. The adjacent is 2. And then the square root of the sum of the squares is the hypotenuse. But that is actually going to be the original guy. It's going to be x plus 2 all squared plus 2 squared. And so that's our triangle. So from that, we can figure out that our secant of theta is going to be, well, secant is hypotenuse over adjacent. So that is going to be the radical of x squared plus 4x plus 4 over 2. And we can also see, well, the tangent, we already know what the tangent is. The tangent is x plus 2 all over 2. And so we actually just plug that in. The integral is ln of the square root of x squared plus 4x plus 2 all over 2 plus x plus 2 all over 2 plus c. Now, let's move that down a little bit. So that would be your answer here. If I call this I plus 8. Okay, that's your guy. Now, here's something to note. In a text, the answer may be written as, so for something like this, I can kind of tell you just by having seen a lot of textbook, chances are they wouldn't write the answer to look like that. They would write the answer to look like this. And I want to know, does anyone see why that would be okay? Say you work through this problem, you got to this point, you got the answer which was in white, and then you check in the back of the textbook to see if you were correct, and you see that answer in the red box. Is that okay? What's going on here? No, it's not because of 1/2 plus 1/2 is 1. Because the halves, one of the halves is attached to this thing, and the other half is attached to the x plus 2. So they're unlike terms. So you can't really add the halves like that. But you could add the fractions. So if you have ln of x squared plus 4x plus 8 plus x plus 2 all over 2, this is over 2. Okay, so both have the same denominator. What does that mean? Well, you can add them, but it's not going to be, you can't add the halves. You can add the two fractions and put everything over 2. And what does that allow you to do? Law of logs. So what does the law say? This is going to be ln of, well, remember log of a division is log of the numerator minus log of the denominator. So this is going to give you this. Minus ln of that. And then this part here, this is just a constant. So they would just absorb this into the plus c. So that's just something I want you to be aware of. Sometimes you're checking your answer. Now, when it comes to integration, you can have answers that are valid that look way different, radically different, pardon the pun, but they are both correct and equivalent answers. Sometimes though, just a simple simplification can make things look a little bit nicer. It's a lot nicer to actually type something without the fraction than to actually type something with a fraction, especially when you're using something like LaTeX. Getting a fraction is the whole code. And usually when people are typesetting these things, they go with the simpler one to type up. So I just want you guys to be aware. You still have to remember all your algebra rules, your log rules, your trig rules, all those things. And you should be able to see that you can simplify your answer to get some other answer, etc. Just want you to be aware of that. It's a very common thing to happen. So, all right. Okay, so that's how we would have gotten through that one. Let's, where are the other questions? There we go. Here's another. Let me enlarge this one too. Okay. Let's move this guy first. No, I can't. Move this guy first. Now enlarge this. Put this guy back. Okay. Yes, that's a basic law of logarithm. ln of a divided by b is ln of a minus ln of b. And so that's works for any log, not just the ln. All right. Next one. What do we do here? Um, 4x squared equals secant theta? No. Remember, look at the table. There's a very special form you should go from and then go to. Right, so it's 2x equals tan theta. So one, it's not a secant because there's a sum. And secondly, you have to be aware, you're not setting the square equal to the trig function. You're setting what's inside. You're setting the base. This you'd realize is 2x all squared plus 1 squared. So the inside, that's your variable. The 2x is like your x from the table. So it's x equals a tangent theta. So that is the correct trig substitution, right? So there was a problem in the quiz yesterday in the bonus section where I simply asked you to state the correct trig substitution. It's not only just, you don't have to just know how to do trig substitution, but you do have to know how to start one off. What is the appropriate thing to actually substitute, right? You need to go from a situation where, so like in here, this here is like your x, right? And this here is like your a, and you have to go from, if you see like x squared plus a squared, then the substitution becomes x equals a tan theta. So you have to be careful. Okay, so 2x equals tangent theta would be the correct substitution. Now, once we do the substitution, we just differentiate both sides to get the differentials in play. And so you realize that your dx is now 1/2 secant squared theta d theta. Then you would simply plug this all into the integral. So you would have 1/2 secant squared theta d theta over the square root of, well, if my 2x is now tangent theta, then that's just going to be tangent squared theta plus 1, which is secant squared. So the radical of that is secant. And so once again, this is the integral of secant. Because this guy in here is secant squared. And then you take the radical of it. So you just get secant. Secant squared divided by secant is secant. So we have that, okay, by just plugging in our substitutions. We saw this one earlier. Integral of secant is ln of the absolute value of secant theta plus tangent theta. And now we go through and we do the back substitution. So we know that 2x was equal to tangent theta. This means that it's already isolated. Your tan theta, you think of it as 2x divided by 1, which you think of that as opposite over adjacent. You can draw the triangle, opposite, adjacent. This would be the square root of this squared plus that squared by Pythagoras' theorem. So you have that, which means I can talk about what the secant is. The secant is going to be hypotenuse over adjacent. And we already know that the tangent of theta is going to be 2x. And so I is equal to 1/2 ln of 4x squared plus 1 plus 2x. And that's our guy. And let's call this I. You don't have to use a triangle for back substitution. I think it's the quickest way to see what the back substitution would be. But you can just use regular trig identities. So if you know that tangent is this, then you know that 1 plus tangent squared would be secant squared. So if you take this squared plus 1, you get secant squared, then you take the radical of that, you would get secant. So you can actually figure out that secant just using trig identities. However, the human brain loves pictures. So if you can draw a little picture to figure something out, I would more often do it than not. The triangle is just a way to visualize and apply the trig identities. Right? Because it's just mentally, it's going to be more exhausting for while you're doing a trig substitution to be thinking of all these trig identities in your head all the time, instead of just looking at a picture and using SOHCAHTOA. So it's not the only way to do it. It's I would say, psychologically speaking, it's the easier way though. Let's actually look at the others. Boom. So hopefully those of you who were confused are starting to get it more now. Point of doing all this practice is for you to really get used to it. Okay, all right, go. Maybe someone who hasn't participated yet can tell me what you'd want to try with this integral. So we have 1 over x squared plus 1 to the 3/2 power. Now, if it was just 1 over x squared plus 1, we already know the answer. That's the inverse tangent. But now we have a 3/2 power on the denominator. Regular substitution is not going to work. Can't really simplify. Yeah, it's not a basic rule. So what do? What's the appropriate trig substitution? Right, x equals tangent theta. Then your dx, let's just call this I for now, just in case you want to do it later. Dx is equal to secant squared theta d theta. This means we can start to plug these guys in. Your dx is going to be secant squared theta. Yeah, you made it beat you. Okay, and in here, we're going to have tangent squared theta plus 1 because your x is tangent. Now, of course, that is going to be, on the other hand, inside here, you're going to have secant squared theta by the trig identity, and the 2's are going to cancel in the powers. And so now you're going to have secant squared divided by secant cubed. So this is 1 over secant is what we're going to be left over with. How do we integrate 1 over secant? The exponent we simplified by laws of exponents. Right? If you know x to the a raised to the b is x to the a, x to the a times b. So in the same way, if you have x squared raised to the 3 over 2, that's just x to the 2 times 3 over 2. The 2's cancel. And you would get x cubed. So in the denominator here, you just have secant cubed. And yes, as we see in the comments, 1 over secant is just cosine. So you'd integrate that, you get positive sine. Students often messed up the sign. Lots of signs, okay. Students often mess up the sign of the sine. Okay, so the answer here is just sine of theta plus c. And now you'd have to do your back substitution. You know that x is equal to tangent theta. And so this means that we can have a triangle. Tangent is opposite over adjacent. So this is going to be the square root of x squared plus 1. And so from that, I can find the sine function easy. Sine of theta is opposite over hypotenuse. So this means that my integral is going to be x over the square root of x squared plus 1 plus c. And that is that guy. Okay. I'll pause here if anyone needs to continue copying, take a screenshot or whatever. That's how we do that one. Now let's move on to the next one. So the next one is a definite integral. And remember what I said, you always want to change the limits on these guys. Changing the limits is going to save you from having to do like this section over here, which sometimes it's short and it's not a big deal. But as you can see from previous examples, sometimes it's not so short. There's a lot of stuff can happen right here. Sometimes you want to save that. You don't want to save that work. Work smarter, not harder. Okay, but so far, let's look at this guy. How do we actually do the integral? Appropriate substitution. See if we're paying attention here. No. So the trig function we're looking for here is a secant. Yeah, for sure. Every time you're doing a trig substitution for a definite integral, you definitely want to change the bounds. So here, and I'm going to show you guys how to change the bounds here. So here, x equals the square root of 3 secant theta. You should be able to see that that is the correct substitution. Now, as I mentioned here, boom, always change the bounds. When doing trig sub. How do you change the bounds? Well, you actually use the original equation. So here, you notice that your x is equal to 2 and radical 3. X is ranging on this interval here. So then you just simply say when x equals radical 3, we're changing the lower bound. This means that radical 3 is equal to radical 3 secant theta. This means that secant theta is equal to 1. This, of course, means that your cosine of theta is equal to 1, which means theta equal to 0. Then, let's move this chat box out of the way. Then, when x equals 2, this means that 2 is equal to radical 3 secant theta. This means that secant theta is 2 over radical 3. This, of course, means that cosine of theta is radical 3 over 2. And this, of course, means that your theta is pi over 6. Okay, so of course, you should remember how to find angles. Just remember everything you've ever learned in pre-calc and algebra. That's basically the idea. So here, I'm not sure your question. I just actually did the calculations here. So when your x is radical 3, your theta is going to be 0. That will give you the theta value. And when your x is 2, your theta value is going to be pi over 6. And then you're going to be able to just actually plug these guys in once you start substituting everything. So now we're going to start substituting everything. We have to find the dx so that we can substitute that. The derivative of secant theta is secant theta tangent theta. And so now we're going to have the integral. Now the integral, we're going to go from 0 to pi over 6. Because we changed it. We changed it to those numbers. Right? So we're plugging in the limits that we changed here. Oh, I changed these colors here. And now let's actually just plug in. So under the radical, what are we going to have? We're going to have 3 secant squared theta minus 3 under the radical. Underneath, we have x. X is our radical 3 secant theta. Then we're going to change our dx, which is radical 3 secant theta tangent theta. So this is our new integral. And now we just want to compute that. Now, what's under here? Secant squared minus 1 is going to give us tangent squared. Take the radical of that, so we just get tangent, and then we have the radical 3. So we have the radical 3 tangent. In the denominator, we have radical 3 secant theta. Then we multiply by radical 3 secant theta tangent theta. The radical 3 cancels this radical 3. This secant cancels that secant. And we end up having the integral of 0 to pi over 6 of radical 3 tangent squared theta. All right. How do we integrate tangent squared? Right, use the trig identity. You'd rewrite that as secant squared theta minus 1. And the integral of secant squared is tangent. The integral of 1 d theta is theta. And here now you plug in the numbers. So fundamental theorem of calculus, this is going to be tangent of pi over 6 minus pi over 6 minus tangent of 0 minus 0. So what is tangent of pi over 6? No. It's 1 over radical 3. So remember, we have a table, and again, this is something that you would have learned in pre-calc or whatever. Theta, sine theta, cosine theta, pi over 6, or that's 30 degrees, pi over 4, it's 45 degrees, pi over 3, that's 60 degrees. Count up from 1 to 3 with sine, 1, 2, 3, backwards with cosine, 3, 2, 1. Take the square root of everybody. Don't have to take the square root of 1 because that's just 1. Then divide everyone by 2. And that is that. Now, of course, to get the tangent, you divide the number in the first row by the number in the second row. For pi over 6, the tangent of pi over 6 is just going to be the sine of pi over 6 divided by the cosine of pi over 6. So that's just going to be 1/2 divided by radical 3 over 2. The halves cancel, and you just end up with 1 over radical 3. So you would get radical 2 over 2. That is actually the tan inverse of pi over 4. So that is going to be 1 over radical 3. Tangent of 0 is 0. And so we would have here 1 over rad 3 minus pi over 6 is going to be the answer. And so you can look at this like 1 minus rad 3 pi over 6 or something like that. Either way. Now, notice here that I didn't have to do, no, there's no plus c because it's a definite integral. But notice here that I didn't have to do a back substitution. I didn't have to do that whole triangle and converting the trig functions back and getting an answer in x because I changed my limits. So I didn't need to actually do that. So once I get here, these are the numbers that correspond to the theta. I can plug these directly into the theta. The old limits, I couldn't plug in the 2 and the radical 3 into theta because they're x's. And so here, you can notice that we can skip the back substitution. Yeah, you have to change the bounds. I wouldn't say it's the same amount of work. I mean, with enough practice, this is almost automatic. Right? I mean, I wrote it out here just to be more explanatory. But like, I wouldn't even write this out all the time, right? Because you would have memorized that table for trigonometry so well, and you know it so well, this knowledge is almost automatic. It's not something you have to construct. Whereas with the diagram, you pretty much have to construct that for a case-by-case basis. The diagram is going to be, in theory, different for every problem you see. However, cosine of 1, theta is going to be, cosine of 0 is what's going to give you 1. That's always going to be true in all scenarios. So this here is a lot more automatic, which means you don't have to write down as a lot, which means your brain is going to access that information quicker. Assuming you have all the stuff memorized that you should have had memorized from a couple years ago. So, well, there's a lot of trig in everything. Trigonometry is a very important topic. So it's actually a good thing that there's a lot of trig in calc too, because students tend to forget all their trigonometry and then they don't know it when they need it. All right, here, this one. What do we do here? Complete the square, right? So you have a very weird thing under the radical. Of course, a substitution is not going to work. It doesn't look like a rule, blah, blah, blah. All that good stuff. You go through, run through that all in your head. You decide on against every other method that we learned so far, and then you settled on maybe a trig sub can work because it's a quadratic. It's not in the right form though. So what you're going to do is you're going to complete the square. Now remember how to complete the square. You need the coefficient of the squared term to be positive, so you have to factor out a negative sign. Then what you have to do is you have to add half the coefficient of the x term and square it. And in this case, we have to subtract that thing because we don't want to change the value. This allows us to, the first three terms will become the complete square. It's 2 plus the base of that squared minus 4. So we have that. And once I distribute the negative sign, that is going to look like the radical of 4 minus x plus 2 squared. So that's what the complete square look like. So that is in a form where we can do a trig substitution. What's the appropriate substitution? No. A lot of guesses. No. You guys are just calling things out now. Think, grasshoppers. Remember your training. Remember your training, grasshoppers. Don't get anxious. Don't start freak out and just, oh my God. Just think. Yes, x plus 2 is equal to 2 sine theta, right? This here is like your x from the general rule. This here, this is 2 squared and the 2 is the a. Right, so that's the appropriate trig substitution. Differentiating both sides of that, I would get this, and then let's call this guy I in case we want to use that later. And then we just start plugging in everything. So the dx is going to be 2 cosine theta d theta over the radical of, we're going to have 4 minus, the x plus 2 is actually 2 sine theta, so this is 4 sine squared theta. Now you're going to realize that, of course, for 1 minus sine squared is cosine squared, so under the radical, you have 4 cosine squared theta, and you take the radical, so that just gives you 2 cosine theta. And on the top, you have 2 cosine theta d theta. This is just the integral of 1 d theta. And so you integrate that, you're just going to get theta plus c. And this is going to be, here you don't really need any extensive back substitution because your theta is just going to be this sine inverse here. And there was also another way that you could have seen that. So maybe I'll just mention that while we're here. So here's something you could have noticed. Another way to see this. Right. So assuming you went through and you memorized all the basic rules and you know them very well, when we had this point right here, one thing you could have done is you could have factored out a 4. Notice that this would give you 1/2 on the outside over, this would be the square root of 1 minus x plus 2 over 2 all squared. So you could have factored out a common 4. You would end up with something that looks like that. Then you could do a substitution, u equals x plus 2 all over 2. Your du is going to be 1/2 dx. This means that 2 du is going to be your dx. So you go back and you plug that in. So you have 1/2 times the integral of 1 over the radical 1 minus u squared times 2 du. The 2's are going to cancel. And then here we're just left with the, undo. Here we're left over with the square root of 1 minus u squared du, which as we now know is actually the sine inverse of u. And your u was the x plus 2 over 2. So you would have sine inverse of x plus 2 over 2. So technically, this is one you could have done without a trig sub. However, the students who aren't so sharp on their algebra probably wouldn't have seen that, and it's not bad getting away without it. So you could do a trig sub as well. So I would think a problem like this, most students would actually go after the trig sub as opposed to doing this. But this is a nice way to do it as well. So another way to see the answer. Okay, let's keep going. Let's keep going. Let's keep going. Where are the other examples? They're way up here somewhere. Okay. Okay, how would you do this one? Yeah, integration is pretty cool. It's harder, it's challenging, but it's a nice kind of challenging. Hopefully you feel that way. I don't know. But you do tons of practice, you'll eventually start to like them, I think. You guys know that MIT has like integral competitions? We just have 2 people going at it. They
Yes,
give you a
I've
random.
seen it. Well, Jhevon, yep, I've seen it. If you go to YouTube, like, you'll see an integral
Yeah.
competition, like, with the,
Yeah.
with the board, the chalkboard, and asking different type
Yeah.
of integrals that no one
Yeah,
can
you
solve.
have two dudes standing on a chalkboard and they give them an integral. And they're, of course, it's an integral where you're just with Calc 2 alone. Typical Calc 2 student won't do well in this, but yeah, they literally have like an integration D. It's crazy. Anyway, how would you do this one?
So, well, I would say that, for x over the square root of 4 minus x squared, you would do like, you get x over 4 subtract 4 sine square and theta, and therefore, your x should be 2 sine theta. How would you
Okay.
approach this problem? But however, what you would get and end up actually, you would get 4 cosine square theta square root 2 cosine theta. And however, the derivative of x, which is 2 sine theta, would be 2 cosine theta. However, if you also the dx of 2, the dx would be 2 cosine theta. Therefore, cross cancel 2 cosine theta, you would get 2 cosine theta. The integral would be 2 sine theta. And if you were to think about, like, draw the right triangle, what you would have is that, would have 4 as the hypotenuse and the x as the adjacent. You would have the angle, and therefore the square root would be 4 minus x squared. And therefore, if you were to think about the sign, it would be 2 times 4 minus x. Okay, square root 2 times square root of 4 minus x squared over 4. Therefore, you would get 4 minus x squared over 2 plus c.
Yeah.
And
So That sounds right. You gave a couple ways of doing that, but actually, as people said in the comments here, this is a trick question. Not trick question in that I didn't want you to do it. Trick question in that I would not use a substitution here. Regular substitution is what we would do. It's the way better option. So I wouldn't do a trig sub. The first thing you should have noticed is that, hey, I could just let u equals 4 minus x squared. Or better yet, u squared equals 4 minus x squared. You can make quick work of that. So that's 2u du is equal to minus 2x dx. And so you have u du is equal to minus u du is equal to minus x dx. You just go and you plug that in. So the integral would become minus u du would replace the x dx. And under the radical, you would have just u. So this is just minus 1 du, which is just minus u plus c. And then you would have your u is just the radical of 4 minus x squared. So substitution is the much faster method here. And that was something that you're supposed to see. Now, this is kind of segueing into this little comment that I wanted to make right here. Similarly, for this guy right here, hopefully you didn't try doing this using trig substitution. I didn't try it, but I assume it's going to be a kind of annoying to actually do it. Again, this is another regular substitution. Regular substitution is the better method here. So again, we would do something like, because we can notice here that this guy is going to be, I can think of this as x squared times x dx over the square root of x squared minus 3. Do something like u squared equals x squared minus 3. My 2u du is going to be 2x dx. You can cancel the 2's from both sides. And you go here and you start plugging those guys in. So here, your x squared is u squared plus 3. The denominator is u, and your x dx is u du. These guys cancel. And this is just the integral now of u squared plus 3 du. Power rule. And then you plug that guy in. So this was x squared minus 3. So this is x squared minus 3 to the 3 halves over 3 plus 3x squared minus 3 to the 1/2 plus c.
Professor, I had a question.
Yes.
How do you determine whether or not it would be better to do a u substitution versus a trig substitution?
Right, to trig sub or not. So that is what I'm going to turn over to you guys now. What do you guys think? Based on these two examples, right? So you can take a picture of that or write it down, x cubed over the radical of x squared minus 3. Take a picture of this, x over the radical of 4 minus x squared, and compare it to something like this or something like that, or like any of the previous examples. What was the difference between these two problems here? Why would you know to use a regular substitution as opposed to a trig substitution? Can anyone give me like a criteria they would look out for, something that they would notice, something that jumps out to them with these two, the last two examples that wasn't true for previous examples? So someone says there was an x in the numerator. Well, in this case, there's an x cubed in the numerator. And sure, you can say, well, yeah, Jhevon, but you could factor off an x. Well, hold on. What if I had an x to the 4th? would a substitution still have worked? Because you can say, well, you can factor off an x. Is the ability to factor off an x is what's important? Would a substitution still work there? So the difference in the power is 1. That's another guess. So what about this guy? I submit to you that if it was x to the 5th over x squared minus 3, I'd still use regular substitution for this. So saying there's a difference of 1 is not really what you want to think about. Any other guesses? So here's when you do not use. There is an odd power of x as a factor elsewhere. Now you can think of positive odd, but could also work for negative odd, could also work for negative odd powers as well. But we'll usually need another technique, which I haven't taught you yet. But that's basically it. So technically speaking, there was an example up here. Where was that example? Technically speaking, this example here, we didn't have to do a trig substitution. However, there is a technique. I haven't taught you the technique that you would use to do this without a trig substitution yet. So you probably wouldn't have seen how to do that yet. But there is a way to start off with this guy with a regular substitution and then find the answer another way, which I will show you eventually. I'll show you guys pretty soon. But so far we haven't had the power, we don't have the technique to deal with a situation where the odd power of x is in a denominator, right? Which means it's like a negative odd power. It's an x to the minus 1. However, once there's a positive odd power, notice what that means. Once you have a positive odd power, what that means is when you factor off an x, right, you're going to have an even power left over. And because the trig substitution substitutes an expression with an even power, you can rewrite that even power in a nicer form, right? So I would use trig sub if we were in a situation like x squared over the radical of 1 plus x squared. Or I would use it like if I was in x to the 4th over the radical of 4 minus x squared, etc. Right? But I would not use a trig sub if I was in a situation like x over the radical of 1 plus x squared. That is a more obvious one. That's a typical example. But even if we go higher, if I had like x to the 9th over radical of 1 plus x squared, or x to the 5th, or x to the something like that, I would use a regular substitution. The fact that there's an odd power of x elsewhere makes odd power of x means a regular substitution will work. And regular substitutions tend to be a lot nicer to pull off than trig substitutions. In fact, I would encourage you guys to redo this problem using a trig substitution, and you can tell me what you would like to do better, right? Here we get to the answer in 3 lines, right? So that's done. So once you have an even power, if you were to factor off an x so that we can get the substitution to work out, we would be left over with an odd power of x. And because the trig substitution it's fundamentally based on even powers of x, has to look like a squared minus x squared, or a squared plus x squared, or x squared minus a squared. There's an x squared, quote unquote, in the general formula. So it means that if you are left over with an odd power of x, it's going to throw a radical into the mix once you try to solve for the x, the odd power. And so that means it's going to be a lot harder. So I would use a trig sub if you're in a situation where you'd like to do a u sub, but you realize that the thing you would substitute has an even power, and there's an even power factor elsewhere in the function. That means a regular substitution is not going to work out. If you try to do a regular substitution with this guy, if you did like a u equals 1 plus x squared, then what you'd realize is that your x would become, well, it's going to be u minus 1, and then you'd have a radical, and it's plus or minus. And so if you did, your du would be 2x dx, you would have 1/2 du would be x dx. And so when you start to plug that in here, you would end up with 1/2 du, but you'd be left over with another x here because it was an x squared in the numerator. So that's going to give you the radical of u minus 1. And then in the denominator, you're going to have that radical u. And this guy is harder. It's going to be much harder than if you had to just done a trig sub. That guy's hard to deal with. And so, yeah, when to use trig sub, when not to use trig sub. I would avoid trig sub if there's an odd power of x elsewhere in the function. Now, if the odd power of x is in the numerator, you're good to go with everything I've already taught you. If the odd power is in the denominator, though, you're going to need an additional technique to pull off the substitution usually. What technique is that? Well, I'm glad you asked, proverbial student. It's actually the next technique that I actually want us to start off on. So that was trig substitution, but right now I'm going to get us started on another integration technique. Of course, we're not going to, let me make sure that we didn't skip any examples here. We're not going to finish using this, but I will show you how this new technique is going to work, and I'll leave you with some examples to do. Okay, this is called integration by partial fractions. And we started this on the 9th. Okay, and here's a motivating example. This is the example that we're going to start off with, right? And I'm going to show you why you might realize that this technique is something that you would want to know. So here's an example of an integral. We have 1 over x squared minus 5x plus 6. Now, based on what we've done before up to this point, you'd realize that a regular substitution is not going to work, and simplifying this is not going to work out. How are you going to simplify 1 over that quadratic? If you were to use a trig sub, what you would do is you would need to complete the square. So to get a trig sub, you would want to complete the square. So this is going to look like x minus 5 over 2 squared plus, if you square this, you would get 25 over 4. And so I need to get a 6 minus a 25 over 4. What is that? 6 is that 24 over 4? It's 26 over 4. So this is over here should be like a quarter or something like that, right? So if you were to complete the square, that's what that guy is going to look like. And then you would end up with a situation where you would have to set x minus 5 over 2 is equal to 1/2 tangent theta. Are you guys with me here? Okay. Now, this already, as you can kind of tell here, yuck, right? You have all these fractions all over the place. That's gonna, I mean, yeah, it's doable. I'd rather not do it though. And so, yeah, we don't want to actually go through that, right? We already see that trig substitution can get kind of tedious, right? It's not very nice. But here's something cool. What if we notice this is true? Right? I mean, look at this. Like if I were to take 1 over x minus 3 and subtract 1 over x minus 2, you combine those, you cross multiply, this would be x minus 2 minus x minus 3 over x minus 3 times x minus 2. The top of the x's are going to cancel. You would have minus 2 plus 3, which is just a 1. And when you multiply out the denominator, you get x squared minus 5x plus 6. So it turns out that this fraction here is actually the same as those two fractions there. Right? So what if somehow, using like Jedi mind powers or whatever, we realize that this was the case? Right? I realize that, hey, you see this integral over here is actually the same as that integral over there. Maybe, I don't know if you guys can see this very well. Maybe I can increase this a little bit. What if I notice that this integral over here is the same as that integral over there? So I can integrate this by integrating that, right? Now, if I do want to actually compute this integral, if I call this I, then this means that my I is just going to be, I can integrate the right side. That's just going to be ln of x minus 3 minus ln of x minus 2 plus c. Now, isn't that just nice? Isn't that very elegant? Like in one step, you can say the answer, as opposed to having to go through a trig sub with fractions all over the place, right? Making this, noticing this identity, yes, it's quite poetic. But perhaps more useful to someone in Calc 2 is not only is it poetic, it's easier. It's a lot easier. If someone had noticed this right off the bat, then integration would not be a problem, right? You won't have to go through triangles. You won't have to do any trig integrals. Right? Like that was very, very easy. So you can start out with an integral where it's like, oh my God, I'm going to have to do this. And then it's like, oh, if I notice that this is that, then it's easy, right? So here's the thing though, how would someone notice that this is equal to that, right? I mean, yeah, if we could do it, if we could do it, I understand that that would be cool, but how would I know to do that? That is what partial fractions is about. Partial fractions is a way to go from a big fraction to a bunch of smaller, a sum of smaller fractions, right? This is called partial fraction, right? So for this trick to work, we have to realize that this is equal to that, right? Now, when we do this, we write a large fraction as a sum of simpler fractions. You say you have done a partial fraction decomposition. The smaller fractions are called the partial fractions of the original fraction. So here, let's move these guys up a little bit. So these guys here, these two here are called, these are the partial fractions of. One over x squared minus 5x plus 6, right? And by the way, Wolfram Alpha knows how to find partial fractions. If you were to type out in English, find the partial fractions of, and then you type this guy, Wolfram Alpha will return that as the answer. So it knows how to do it. You can have calculators that check, that can do this, right? So it is a known method. It's well, everyone knows about it, okay? So what I'm going to teach you is how, as a human being, for you to go from this situation to that situation, right? So that's what we're going to cover now. And it turns out that there's a standard strategy that can actually go from this situation to finding its partial fractions. However, the first thing you want to know is, can I actually accomplish this, right? When do we know that we can actually do this? It turns out that there are some fractions that do not have partial fractions, right? So the first question we need to ask ourselves is this even possible? How do I know that when I'm looking at something, I have the ability to actually get this done? Because you don't always have the ability. If this 6 were a 1, for example, then you're out of luck. Then that's a trig substitution problem, right? We kind of lucked out right here that was a minus 5x in the middle term and a 6 in the last term. Okay, so when do we know that we can do it? There are a couple of things you need to look out for. The first thing is, as someone mentioned, yeah, the denominator should be factorable. You should be able to factor the denominator. So that's the first thing. The fact that x squared minus 5x plus 6 factors into x minus 3 times x plus 2 times x minus 2 is a part of the reason why I was able to do this. This tells me that when I combine the two denominators, right, if I multiply the two denominators, I get the general denominator over here. So these two guys are factors of the denominator. So that's the first thing. We need to make sure that the denominator can be factored. If it cannot be factored, then you end up in a situation where the only choice is to complete the square and then do a trig sub, assuming that a regular substitution isn't going to work out. So that is a part of it. Another thing is you have to have a proper rational function. So first of all, it has to be a rational function. Remember what rational function means? Rational function means it's a ratio of polynomials. So you have to have one polynomial divided by another. So for example, if I had 1 over the square root of x squared minus 5x plus 6, then we're out of luck. Then we have to do the trig sub, right? However, I had one polynomial, which is 1, divided by another polynomial. So if I have a ratio of polynomials and the denominator factors, that's good. Another thing, though, is we have to have proper, and it's actually important. That's actually important that we have the proper. Let me put that in bold. Let's maybe even make it red. The proper is an important part. Now, proper means the degree of the denominator. It's the other way around. Typo. The degree of the numerator must be lower than the degree of the denominator. Which I probably should correct that in my prep notes here. Partial fractions. Okay, so once these requirements are fulfilled, however, then this is a thing that can be done. We will be able to take that large fraction and break it up into smaller, quote unquote, partial fractions. So as long as you have a ratio of polynomials, so you don't have any radicals or anything like that, you just have one polynomial divided by another polynomial. Then the denominator of the polynomial can be factored, and the degree of the numerator is smaller than the degree of the denominator, you will be able to do the partial fractions decomposition of the larger fraction, right? So now, once we know we can actually do it, how do we do it? Here's how we do it. Okay, so this is the method of partial fractions decomposition. So this is the method at a glance. These are all steps here, but I do go in and I expand on the steps later on. So here is the method of partial fractions. So what I would say you should do is actually have the entire method written down in one place, So on your formula sheet or your cheat sheet or whatever, you should have this entire method written down. Okay, so this is it. Maybe I can put a box over that because that's an important thing to know. So the method of partial fractions, this is the important thing in this section. Okay, so let's put that in a box. That's the method of partial fractions, okay? So step 1, make sure the function has a factorable denominator and that it is proper. That's the first thing. Before you even start the process, you have to check that the process is possible. Step 2, you're actually going to factor the denominator completely, okay? Step 3, you're going to break up the larger fraction into smaller fractions, where the denominators are the factors from step 2, okay? And the numerators, and this is an important part, the numerator is going to be a generic polynomial of 1 degree less. Now I'm going to explain what it means to be, what I mean by a generic polynomial and what I mean by 1 degree less. We're going to talk about that, but it's very important that it is 1 degree less specifically, okay? And I'm going to show you guys what that has to mean. Now, if any factors are repeated, you must further break down that fraction into smaller fractions where you count up to the multiplicity. And again, I'm going to expand on this step, explain to you exactly what it means. And then you will now be able to, you will now have the big fraction written down in a generic way as smaller fractions. And you have to find the arbitrary constants that are going to show up. On top of that, there is an optional, well, it's optional, but I would highly recommend you learn it. There's something called the cover-up method, which allows you to find the arbitrary constants much quicker in very specific scenarios. And I will talk about that. So this is the method at a glance. Now, once you learn what each of these steps are, then all you have to do is memorize these steps, and you'll be able to get through a partial fractions process, okay? So saying it in English is going to be confusing to someone who hasn't done this method before, so I'm going to expand on each of these steps individually. Okay, let's start with step 1, okay? Make sure the function has a factorable denominator and that it is proper. If it is not proper, make it so. Okay, so the denominator has to be factorable. If it's not, then all bets are off. Like, you can't do it anymore. However, it turns out if it's not proper, you can fix it, okay? So let me talk about some ways in which you can actually fix it if it is improper. So this is when the power of the numerator is greater than or equal to the power of the denominator. And there are 2 ways that you can remedy this situation. So here's an example. I have 2. We're going to do this. Here's an example. So here, this is rational, but improper. How can I make it proper? There are 2 main ways. One is algebraic manipulation. The other one is polynomial long division, which again is something that you learned from pre-calc, so it's going to be another throwback Thursday or throwback Tuesday. But I'm going to run through that quickly. So here's one way, algebraic manipulation. So there is something that works a lot, not all the time, something that often works. Get the denominator in the numerator. Meaning, whatever you have to do to get the denominator in the numerator, meaning if you have to add or subtract something, if you have to multiply and divide by the same thing, whatever algebraic trickery that's valid and it doesn't change the value of the fraction that allows you to do that, you can do it. So for example, if I have x squared plus 1 divided by x squared plus 2, I can get the denominator in the numerator by writing it in and then correcting for the thing that I just wrote in. So I can add and subtract a 2. This allows me to get the denominator, which is x squared. This allows me to get the denominator, which is x squared plus 2 in the numerator. Okay, so here I just add and subtract the 2. Now, what does that allow me to do? Notice what's going to happen here. now you will have, now you will have x squared plus 2 minus 1 in the numerator. This allows you to actually, let's move this out of the way. This allows you to actually break the fraction into two parts. You can now take this part of the fraction and separate it from this part of the fraction. So here you would get x squared plus 2 divided by x squared plus 2 minus 1 over x squared plus 2. This is just 1 minus 1 over x squared plus 2. And you will now notice that this is the same as the original, and the last fraction is now proper. And there you go. And again, this is a skill that you don't, once you use it a lot, you'll get very quick at doing it. And you can, normally students can jump from this step right to this step, or normally they can jump from this step to at least this step relatively quickly without even writing all this out. With a lot of practice, you'll actually get that. But that is algebraic manipulation. Find a neat way to get the denominator in the numerator. Okay. Here's another example. And these guys are going to be in the way, so let me move them. Lots of stuff here. Why? And these are the examples I'm going to have you guys do. After I finish teaching you the method, we're not going to have time to go through these examples, but I will leave them in the notes for you to actually try these examples. These are all examples that we can do using partial fractions to help us. I think that's everyone. Okay. Move these to the side. Okay, so here's another example. Yeah, they look fun, right? You guys are gonna have all the fun. All right, so here's another example. I have x cubed plus x over x squared plus 2. Again, it's not proper. However, we can try to find a way to get the denominator in the numerator. What would that take in this situation? Well, notice that x is a common term in the numerator. I can factor that x out. And again, I can do the same thing. Add 2 and subtract 2. So now I got the denominator in the numerator. So this tells me that this is actually x times x squared plus 2 minus 1 over x squared plus 2. This is x times 1 minus 1 over x squared plus 2. And this just becomes now x minus x over x squared plus 2. So there we go again from a situation where we don't have a proper fraction into a situation where we have a proper fraction. Okay, and that's just by using algebraic manipulation to get the denominator in the numerator. Another option is polynomial long division. So again, this is something that technically we should already know how to do, so I'm not going to teach you this. You can check if you forgot how to do this. You can either Google it, look it up, or you can actually look at my Math 195 lectures. I teach this in there, so you can find the right video for that. So this means, so I'm going to redo this example here, but I'm going to use long division to do it. Synthetic division is also an option, but synthetic division is limited in a way that long division isn't, and because synthetic division only works with monic polynomials. So that's automatically a reason why I would choose long division over synthetic division. Another one is that I always just forget how synthetic division works for whatever reason. I learned long division, I liked it, I ran with it, and so yeah. So notice what we have here is that we are taking x squared plus 2 and we're dividing it into the x cubed.
Polynomial
plus
long
x.
division, right? Like,
Yes,
we
polynomial
divide,
long division.
x cubed plus x with x squared plus 2, and therefore you would multiply x,
Well, hold on, I'm explaining it. So I'm not gonna have you guys chime in here because especially since we're short on time. So I'm just gonna show you what you have to know. One thing that students often forget is you need placeholders. So once the guy underneath the division, you need to hold the place for all powers. So even though there's no x squared, I would write in a 0x squared. And even though there's no constant, write in a 0. So you need placeholders for all powers of x under that guy. Okay, so once you have that, here is how you continue. You take the first guy divided into the first guy. That is going, so you take x squared divided into x cubed, you're going to be left with x, because x cubed divided by x squared is x. Then you're going to take this guy. Oh, maybe I should actually put that in green. So you'll get that once you divide it. Then you're going to take that guy and you're going to multiply everyone here. Then you're going to put the result below. So x times x squared is x cubed. X times 2x is x times 2 is 2x. And you write that result below, and you're going to subtract that from above. Now notice that you're going to have the x cubed minus the x cubed goes away. Here you're going to have x minus 2x, so this is minus x. And then you repeat the process. X squared into x, you notice that you can't. So this guy here ends up being the remainder. So this here is the remainder. And so now this just becomes the quotient, which is x, plus the remainder over the divisor, because we're essentially doing long division. So this implies that x cubed plus x over x squared plus 2 is going to be the quotient, which is the x that is on top. So it's the quotient plus the remainder over the divisor. And so that, you'll notice, is the same as the answer that we got earlier. So a couple ways to get that. Okay, so that's polynomial long division. Again, if you don't remember that, you have to review that on your own time. I don't want to get into it. So that is a situation where you don't have a proper rational function and you want to make it proper. Let's look at the other scenarios. So step 2. So that's step 1. Make sure you have a proper rational function. If not, you can make it proper by doing that. Step 2 is factor the denominator completely. This is self-explanatory. There's nothing else for me to tell you here. Remember all your factor techniques. I will say this. Remember how to use the rational roots theorem. So I'm not going to remind you of what that is at this point, but when you go, I was going to say when you go home, you guys are already home probably. But definitely look up the rational roots theorem to remind yourselves of that. So, but that step is self-explanatory. Factor the denominator using whatever technique you have. Now, here's the other step, which this is especially confusing when written in English. So let me explain to you guys what the third step is about. Third step, part A, step 3. Break up the larger fractions into smaller ones where the denominators are the factors from step 2. The numerators are generic polynomials of 1 degree less. What does that mean? Okay, so here is a situation. This is a proper rational function. Notice that the denominators are factored. And so now I'm in the situation where I come from step 2. What to do? This means you're going to break this up into smaller fractions where the denominators are each factor. So the denominators here were x and the factors here were x and x plus 2. That's going to be the denominators of the smaller fractions. What should the numerators look like? the numerators are going to be generic polynomials of 1 degree less than the base factor in the denominator. Notice that the base factor in the denominator here is degree 1, which means the numerator must be degree 0. A degree 0 polynomial is a constant. So now you have to just put a generic constant. Normally we use a, uppercase A, right? Similarly, the base of this is x plus 2. That has degree 1, which means the numerator must be degree 0. B, that is a generic answer. Okay, let me do another example, and then you can ask me if this confuses you. Here's another example. Let's say I had a fraction, I factored the denominator, and now it looks like that, which means this is going to break up into 2 smaller fractions where these guys are the denominators. It cannot be factored any further. On the first one, the denominator is degree 1. The numerator must be degree 0. So that's just A. On the second factor, the denominator is degree 2. It's a quadratic, which means the numerator must be degree 1. It must be linear. So it must look like a straight line, bx plus c, right? So I write out a full generic 1 degree polynomial. The coefficients I don't know, that's why it's called generic, but that is going to be what the second fraction should look like. Do we all get it? Okay, all right, so we got that. All right, Fahim, you said kind of. All right, try your luck on this one. What do you think this one is going to break up into? Let me see if you understand or not. What do you think, Fahim? Right, the denominators are x and x cubed plus 7. Neither of those can be factored further. What do you think the numerator of the first one is going to be? A, all right? Plus, what do you think the second? Okay, so that is a good start, but it is not a generic second degree polynomial. What about the linear term? What about the constant term? Right? In general, when you think of a quadratic, you think of something that looks like this, right? You must have the option of having numbers here, even though there might not be, right? So that's what I mean by generic. So having the bx squared alone is not enough. You need the linear term and the constant term. So the denominator is a cubic, which means the numerator must be a generic or a general form of a quadratic, right? Okay, got it, good. So that is step 3, right? So first step, make sure it's proper. If not, do long division or whatever if you have to. Now, it's possible that after doing this, you don't even need this method, but you might. The next step would be to factor the denominator completely. Once you have that, you now can break up the bigger fraction into smaller fractions where the denominators are each of the factors and the numerators are specifically 1 degree less. Okay. Now, here is part 3, part B. Sometimes you have repeated factors. Whenever you have repeated factors, like here, you see there's an x plus 1 factor, but it's repeated, it's being squared, or there's an x plus 1 cubed, it's repeated, it's multiplying itself 3 times. These are called repeated factors. Now, whenever you have repeated factors, you have to actually count up to their multiplicity, and here's what I mean by that. So here, you have the base factors are x and x plus 1. But notice that you don't just have an x plus 1, you have an x plus 1 squared. So what you actually have to do is you have the x plus 1 to the first power and the x plus 1 to the squared power. Okay? The base factor here is of degree 1, so that's A. 2, the base factor here is of degree 1, so that's B. Here, the base factor is of degree 1, so that's C. Notice that I mentioned here the base factor, which means I'm talking about the guy that's inside the parentheses. So here I'm referring to the x squared plus 1. You ignore the square for this scenario. And I'll explain next time why it works out this way. But for now, that's the idea. Here's another one to see if you get what I'm saying. Here, I have 2x times x plus 1 cubed. So again, I'm going to break this up. The first one is x. This is x plus 1 is the base factor, but it's cubed. So I'm going to have x plus 1, then x plus 1 squared, then x plus 1 cubed. This is what it means to count up to the multiplicity. On the numerator, generic polynomial 1 degree less than the base factor. Again, the base factor is the guy that's inside the parentheses. So these are all degree 1s, A, B, C, D. All right, someone actually tell me about this one. What do you think this one is going to break down into? So here you realize the base factors are x and x squared plus 1. However, the x squared plus 1 is repeated, which means you have to count up to the multiplicity. Now, x squared plus 1 doesn't factor, right? So this is x. The next one is going to be x squared plus 1. The next one is going to be x squared plus 1 squared. Base factor here is of degree 1, which means the numerator needs to be degree 0. The base factor here is a quadratic. The numerator needs to be linear. Base factor here is a quadratic. The numerator needs to be linear. That is the partial fractions decomposition. Now you might wonder, why does it actually break down this way specifically? So here's an example of why it would break down this way. So let's say I have like 1 over, say, x plus 1 all squared. So technically, if I apply the previous method of seeing, oh, there's a quadratic in the denominator, so the numerator must be linear, you can do that. But it's nice when you write it as a linear function where you think of the inside as the variable. Think of this as the variable. Now, what that means is the linear factor that you would put on top is going to look like the following: a x plus 1 plus b. So you don't let x be the variable. You think of x plus 1 as the variable. And so if you put a linear one on top, what you'll realize is that this now breaks down into a x plus 1 over x plus 1 squared plus b over x plus 1 squared. This situation, you're going to have the x plus 1 cancels that. And so you will have here a over x plus 1 plus b over x plus 1 squared. So you end up to break it down, to break down something like this into smaller fractions. It turns out counting up to the multiplicity is the way you're going to do it, right? Just by thinking of the base factor as the variable and then expanding this based on the recommendations of 3 part A. You end up having a situation like this unfolding. Now, this leads us to step 4. And of course, we won't get through any of these examples here, but let me just leave you off with this. Step 4, this is the final step. It's not always necessary. There are times when I ask you not to find the arbitrary constant, but the last step is you finding what these A's and B's are, right? So how do you go about finding what the A's and B's are? Let's actually use the method to find out the original guy, the guy that started this whole discussion, that guy, right? So we had x squared minus 5x plus 6. what you're going to do is you're going to factor the denominator because this is actually a proper. Then you're going to break this up into generic factors. So now we've done the first 3 steps. Now, hopefully everyone's with me so far. Okay, now how do you go about finding the a and b? Notice what you have is that this guy, 1 over x squared minus 5x plus 6 is equal to that. So that's what you have at this point. How do you go about finding a and b? Well, there are 2 main methods. So one thing you're going to do is multiply both sides by the denominator on the left. That's always going to be the first step for either method. By doing that, notice what's going to happen. I will have a 1 over here, and on that side, notice that this is what I would have, right? Because the x squared minus 5x plus 6 is really x minus 3 times x minus 2. When I multiply by x minus 3 times x minus 2, the x minus 3's cancel in the first situation and it leaves me over with x minus 2, while the x minus 2's cancel in the second situation and it leaves me with x minus 3. So that is what you can get. So this guy is equal to that. Now here's method 1. To proceed from this stage, one thing you can do is you can, and I wrote this all, I typed this all out, so you'll be able to follow me. So for now, I'm just going to verbally describe the method. One thing you can do is plug in convenient values for the x's that will allow you to solve for the a's and b's. What is a convenient value? Well, values of x that allows you to cancel as many of these arbitrary constants as possible so that you can solve for the remaining ones. So for example, here, x equals 2 is a convenient value. Why? Because if I plug in x equals 2, x minus 2 will become 0, the a is going to die, and I'll be left over with something that's to b, right? I will have here 1 equals a times 2 minus 2 plus b 2 minus 3. This here goes to 0. So I've eliminated the a. Now I just have an equation with the b. Now you get that your b is minus 1. Similarly, x equals 3 is a convenient value. If I plug in x equals 3 into this equation, this guy is going to die, leaving me alone with the a. So I would get 1 equals a times 3 minus 2 plus b times 3 minus 3. This is going to go to 0, and then I would get a equals 1. And so this would mean that my 1 over x squared minus 5x plus 6 is equal to 1 over x minus 3 minus 1 over x minus 2. This here is the a. Right? It was a over x minus 3 and b over x minus 2. And this here is the b. And that is how I figured out this in the beginning. See, that's what we had here. Oh, interesting. Hopefully you followed that. Here's another method, and just give me like 3 more minutes to get through this. When you had x squared minus 5x plus 6 equals a over x minus 3 plus b over x minus 2. Here is another thing you could have done. Again, you would multiply both sides by the denominator on the left. But now, instead of plugging in convenient values for x, here's something you can do. You can actually multiply out. And then you can combine like terms. So we have a plus b times x. And then we have minus 2a minus 3b. So we group all the guys with x's, group all the guys without x's. Now what you do is something that's called equating coefficients. Notice on the left side, I have 0x plus 1, while on the right side, I have a plus b x plus this. This means I can actually equate coefficients. The number of x's on the left must be equal to the number of x's on the right. The constant value on the left must be equal to the constant value on the right. This allows me to set up a system of equations. A plus b must be equal to 0. And at the same time, minus 2a minus 3b must be equal to 1. This is a system of equations, and then again, it's a throwback to algebra class. You have to learn how to solve that. Multiple ways to solve this. You can multiply the top equation by 2. If I call this equation 1, call that equation 2, and then actually add it. Here you would get minus b equals 1. So this means your b equals minus 1. And then this would mean that a is equal to positive 1, since a plus b must be 0. And so again, we end up with 1 over x squared minus 5x plus 6 is 1 over x minus 3 minus 1 over x minus 2. And those guys are the partial fractions. Okay, so we rushed a little bit at the end, but we're about 15 minutes over time at this point. So hopefully that was somewhat clear, but we can run through it again next time. And what I'd ask you guys to do is to actually try to find the partial fractions here using what I showed you so far. And I can show you a shortcut in tomorrow's class that is going to allow you to get some situations easier. But we'll stop there for now. Hopefully you had fun. Go find some partial fractions. Try those examples. I'll leave them in the notes here. And we will kind of wrap up there. So hopefully you understood that. I'll post the notes and the video as usual, so you can try the problems that I left over, and I will we'll pick up with that next time. So thanks for sticking around for overtime, guys, and I will see you guys in the next one.